After a detailed discussion of intrinsic carrier concentration in previous lecture, today we are going to see how we can discuss the electrical conductivity of intrinsic semiconductor. Actually, an intrinsic semiconductor conducts electricity if the temperature is not 0 Kelvin. Actually, at 0 Kelvin temperature, this semiconductor behaves like an insulator. But when temperature is raised, then intrinsic semiconductors behaves as a conductor and it conducts electricity. So how the electrical conductivity depends on temperature of this intrinsic semiconductor, we are going to see in this present lecture. Okay? And in fact, if you will discuss the concept of electrical conductivity of intrinsic semiconductor, the discussion needs the idea of drift velocity and mobility of the charge carrier. So in this lecture, we will also learn about the drift velocity and mobility of electrons and holes, that is the charge carriers of the intrinsic semiconductor. Okay? As you have seen earlier several times that if temperature of an intrinsic semiconductor is 0 Kelvin temperature, then its conduction band is completely vacant. It is completely empty. Okay? So in that condition, there is no electron in the conduction band, that is concentration of electron is 0. Okay? And at the same time, there is no hole present in the valence band, that is concentration of hole is also 0. But this happens when temperature is at 0 Kelvin temperature. And so at 0 Kelvin temperature, there is no free available charge carriers that can conduct electricity, and our intrinsic semiconductor behaves like an insulator. But what will happen or what happens when T is not 0 K? Even if you are talking about your semiconductor at normal room temperature, actually even at normal room temperature, some of the valence bond, some of the covalent bonds, you can say, of this crystal are broken. And when the covalent bonds are broken due to the thermal agitation and the lattice vibration, then some of the valence band electrons are present in the conduction band. And these valence electrons actually come from the valence band. And so they leave behind holes. So in this way you can say when T is not 0 Kelvin, then some of the electrons moves from this valence band to the conduction band, and they leave behind hole in the valence band. So there is now some holes present in the valence band and electrons present in the conduction band when temperature is not 0 Kelvin. It means in this condition N is not 0 and P is also not 0. Here N actually represents the concentration of electron in conduction band and P represents the concentration of holes in valence band. Okay? Actually this charge carrier becomes available due to the thermal agitation and the lattice vibration. Okay? So you can say that at ordinary temperature, an intrinsic semiconductor always contains some free electrons in the conduction band and an equal number of holes in the valence band. Okay? But these electrons and holes in conduction band and valence band, in absence of any external electric field, have actually random motion. Okay? They behave like just free electron and free holes, and so their motions are random. And if electrons will move randomly in conduction band, they will constitute no electric current. And similarly, if holes are moving randomly in valence band, then there will be no electric current due to this random motion of the holes too. So, although charge carriers are now available when temperature is not 0 Kelvin, it is just an ordinary non-zero Kelvin temperature, then charge carriers are available in conduction band and valence band, but are those charge carriers constituting electric current in absence of electric field? Answer is no, because they are in random motion. So, in absence of any applied electric field, you can say that these electrons and holes move in random direction and constitute no electric current. Okay. But now let us consider that an electric field is applied, or you can say that an external electric field is across the specimen of our conductor. So if you see if this electric field E is applied, let us say from left to right direction. Electron which has negative charge, okay, this will experience electric force due to this electric field in opposite direction of the field due to its negative charge. Okay, so the electron experiences electric force Fe in just opposite direction of the electric field. On the other hand, this hole has equal positive charge, and as it has positive charge, so the hole the force experienced by the hole, that is Fh, it is parallel to the electric field. So you can say when we apply an external electric field or we apply a voltage or a potential difference is set up across the semiconductor, then due to the external electric field, the electrons and the holes move just in opposite direction in the conduction band and the valence band. In conduction band, electrons moves in opposite direction of applied field, while in valence band the holes move in the direction of applied electric field. Okay. So in this way, the randomness of the motion of the charge carriers are ceased. Okay. But now they are moving under the electric field which we have applied. Okay. So due to this electric field, the charge carriers experience electric force, so its motion will get accelerated. And due to the accelerated motion, there will be an increase in velocity of the charge carriers. But that this increase in velocity of the charge carriers will not continue indefinitely. Why this velocity will not increase indefinitely? Because during the motion, these charge carriers suffer so many collisions due to some of the obstacles. And what are those obstacles with which our electron and holes will collide? They are actually the atomic nuclei present in the specimen and also the phonons. Okay. So during its motion, the charge carriers collide with the atomic nuclei, with the phonons, and so any other obstacles, okay, present in this semiconductor. And that's why during every collision, the velocity of the charge carrier will get decreased. And in this way, finally, these charge carriers moves with a constant average velocity under the electric field. And that constant average velocity with which the charge carrier moves inside this semiconductor under the applied electric field, that velocity is called drift velocity. And this velocity you have already learned in your lower classes in your course on current electricity. Okay. So drift velocity is what? This is an average constant velocity with which charge carriers moves under the applied electric field. So for drift velocity, completely the applied electric field is responsible. It has no relation with the random motion of the charge carrier when no electric field was applied. This is actually the modified constant velocity of charge carriers under the electric field. Okay? And so the magnitude and the direction of this drift velocity depends on the applied electric field. Actually, it is found that the magnitude of drift velocity of the charge carrier is directly proportional to the electric field. As the electric field is increased, the value of drift velocity also increases. And in absence of electric field, there will be no drifting motion, no this particular type of motion, but there will be random motion in absence of the electric field, and we cannot talk about drift velocity. Okay. So for your convenience, although I have explained everything, and for your convenience, I have written those things here, and you can note down these things in your notebook by pausing the video. Okay. So now let us see. If Vd is the magnitude of the drift velocity of charge carriers, and E is the strength of applied external electric field, then actually Vd is proportional to E. Okay, Vd is proportional to E. And so this Vd is given by the relation Vd equal to mu times E. Here this proportionality constant mu is called mobility of the charge carrier, or it is also called mass mobility of the charge carrier. And you can see from this relation that if we consider that this E is equal to 0, then this Vd will be what? This will be 0. So you can't talk about this drift velocity in absence of electric field. This is actually the velocity acquired by the charge carrier due to the applied electric field. Okay? So completely for this velocity, the applied electric field is responsible. Okay? Now how we can define this mobility mu in a quantitative way? You can see from this equation 1 that mu is equal to Vd over E. And by this relation, you can define this mu. Let us see. When you apply electric field E, or you can say if the strength of electric field is E, then the drift velocity acquired by the charge carrier is Vd. And so when an electric field of unit strength is applied, then what will be the drift velocity acquired by the charge carrier? That will be Vd over E. Okay? So in this way, you can define this mobility as the drift velocity acquired by the charge carrier when an electric field of unit strength is applied. Okay? So drift velocity acquired by a carrier per unit electric field strength, that is called mobility. Okay? So mobility is drift velocity acquired by the charge carrier when the electric field of unit strength is applied. Okay? I think you have definitely understand how we can define this mobility and this drift velocity. Okay? Now actually in case of the pure semiconductor, we have to calculate the electrical conductivity of this conductor, and for that we will need the concept of this drift velocity and the mobility of the charge carrier. Now you can see at 0 Kelvin temperature, you know, this conduction band of an intrinsic semiconductor is completely empty. Okay? And so there is no electron in the conduction band and no holes in the valence band at 0 Kelvin temperature. But the physical state of conduction band and valence band at this 0 Kelvin temperature or near a temperature of 0 Kelvin is entirely different. The conduction band is completely empty, but at 0 Kelvin temperature, although there is no hole in the valence band, but this valence band is filled with the atoms of the material, or you can say the ions of the material. Okay, so valence band is completely filled at 0 Kelvin temperature, and conduction band is completely unfilled, completely empty, completely vacant. Okay. Now, when temperature is raised, you have seen that some of the electron will become free from the covalent bond, and they will move to the conduction band when energy gained by the electron by the thermal agitation or the lattice vibration E is greater or equal to the band gap Eg. Okay. Now the electron moves under the electric field in conduction band, and this hole moves under the electric field in this valence band. But you know, the physical condition of the medium in which electron is moving and the holes are moving are completely different. The electrons move almost in empty region where there is no other thing, and so the motion of this electron is completely governed by the applied electric field. On the other hand, the valence band is almost filled, so the holes are moving in filled band, and the motion of this hole will be governed not only by the applied electric field but also by the field constituted by the ions or the nuclei present in this valence band. Okay? So the physical situation or physical condition of conduction band in which electrons are moving and valence band in which holes are moving are entirely different. And so that you know, I have told this fact earlier to you, that the drift velocity of electron in conduction band, which we will say VDN, and drift velocity of hole in valence band, which we will denote by the symbol VDP, they will be different, they will be not same. Similarly, the mobility of the electron mu n will be not equal to the mobility of the hole mu p. Okay? And if you say that sigma n is the electrical conductivity of our material due to the charge carrier electron, that will be different from its conductivity due to the holes which I have denoted by the symbol sigma p. So drift velocity, mobility and conductivity, all these things will be different for electron and holes, because in nutshell you can say the electrons and holes are moving in the different regions where the physical situations are different. Okay? So I think you have clearly understand this. So, and that fact I have written here for your convenience. You can see in a pure semiconductor, under the influence of an electric field, electrons move nearly empty, mark this, nearly empty conduction band, whereas holes move in nearly filled band. Okay? Therefore, an electron in conduction band is subjected to different conditions compared to a hole in valence band. And thus, the properties such as mobility, conductivity, etc. of electrons in general are in general different from those of holes. Okay? I think you have clearly understood this. Now, after knowing the expression for drift velocity in terms of the applied electric field, now we can find the conductivity of this pure semiconductor. Okay. As you know, this semiconductor has two types of charge carriers. Those are electrons and holes, and due to both of these charge carriers, these materials conduct electricity. So we will calculate the electrical conductivity of pure semiconductor due to the electron and due to the holes separately, and after that we will add those conductivity to get the total conductivity of this material. So first of all, we are going to talk about the conductivity due to electrons. Okay, and for this, let us consider that this Vdn denotes the drift velocity of the electrons in conduction band, and this μn denotes the mobility of electrons in conduction band, and n we have assumed this is concentration of electron in in conduction band, and E is the charge of an electron. Actually, I have taken here the magnitude of charge, not the sign. Now, due to the systematic drift motion of electron, a current will be constituted, and this Jn represents the current density due to drift of electrons. When you say current density, that means the current flowing through unit area, or you can say charge flowing per second per unit area. Okay. Since this Jn is electric charge flowing per second per unit area, so what will be the value of Jn? If you consider that there is a cross section of unit area, A is unit here, and the electrons enter here and leaves from here. Okay. In 1 second, it will travel a distance Vd. So this electron in 1 second will describe a cylinder whose cross-sectional area is 1 and length is equal to Vd. So how many electrons will cross in 1 second through this section? You can see, since number of electrons in unit volume is n and E is charge of one of the electrons, so Ne represents the charge in unit volume, and volume of this cylinder will be A times Vd, that will be 1 times Vd, that is Vd. Okay, so volume is Vdn. Okay, so Jn, which is electric charge flowing per second through unit area, that will be given by Jn equal to Ne Vdn. And you have definitely learnt about this in your course on electricity in 12th level. Okay. So this is current density due to the drift of charge carrier electron. Okay. But you have just learnt that this drift velocity is equal to mobility times electric field. So since mobility of electron has been assumed μn, so Vdn will be equal to μn times E. Now let us put this value of Vdn here in the expression of Jn, and so Jn is given by Ne times μn times E. This is the current density due to the drift of electron. Okay. But you have definitely studied Ohm's law in two forms. One of the forms of Ohm's law in which we write V equal to IR. This is actually called the macroscopic form of Ohm's law, or a scalar form of Ohm's law. On the other hand, the vector form of Ohm's law is written like that. This is J equal to sigma E. This is called microscopic form of Ohm's law or vector form of Ohm's law. So, according to the microscopic form of Ohm's law, this current density Jn will be given by sigma n times E. Actually here, this sigma n is the electrical conductivity of this semiconductor due to electrons. Okay. So actually, I have defined this Jn by two ways. In equation 3, Jn has been defined in terms of the applied electric field in this way. And in equation 4, on the basis of Ohm's law, we have defined the same Jn. So you can compare this equation 3 and 4, and comparing this equation 3 and 4, you can see that at the place of sigma n we have Ne mu n in equation 3. So comparing these two equations, we find that the electrical conductivity of a pure semiconductor due to its charge carrier electron is given as Ne times mu n, where n is the concentration of electron, that is number of electrons per unit volume in its conduction band. E is the magnitude of the charge of an electron, and mu n is its mobility. Okay. So in terms of mobility, you can define the electrical conductivity of this semiconductor for charge carrier electron. Okay. Now actually on the same line, you can define the electrical conductivity of this material due to the drift of holes. Okay. And for this we consider that this P represents the concentration of holes in valence band, and this mu P is the mobility of holes in valence band. Then on the basis of this equation 5, you can say that electrical conductivity of this material due to the holes, if we denote it by sigma P, then that sigma P will be given by P times E times mu P. You can see this has been directly written on the basis of this equation 5. Okay. Here you know P is the concentration of holes in valence band, and E is charge of a hole, which is equal to charge of electron, but sign is different. Charge of electron is negative and charge of hole is positive, but value is same. Okay, and mu P is the mobility of the holes. So in this way we have calculated the electrical conductivity of a pure semiconductor due to its charge carriers, electrons and holes. Okay. Now when you will add these two conductivities, you will get then the total electrical conductivity of this intrinsic semiconductor. So its total electrical conductivity denoted by this symbol sigma, that will be simply equal to sigma n plus sigma p. Okay. And let us put the values of sigma n and sigma p from equation 5 and 6 here, and you can see this sigma will be then equal to E times n into mu n plus p into mu p. So this is actually the expression for the electrical conductivity of a pure semiconductor. And you can see this conductivity depends on two factors. One factor is the concentration of charge carriers, and another is the mobility of charge carriers. But as long as you are talking about the intrinsic semiconductor, you know, in case of intrinsic semiconductor, the concentration of electrons N in conduction band and the concentration of holes in valence band, both are same. We have already learned this. So N is equal to P, and we denote both of these by the symbol Ni, which is actually called intrinsic carrier concentration. This is called intrinsic carrier concentration. So in this equation 7, this N and P may be replaced by Ni, and when you will do this, you can see sigma will then be written like as Ni times E times mu n plus mu p. So this is the final expression for the electrical conductivity of a pure semiconductor. Okay? But just in the previous lecture you have seen the calculation of this intrinsic semiconductor in terms of the energy band gap Eg. Energy band gap Eg, you know This is in fact EC minus EV, and it is called band gap or energy band gap or forbidden energy gap. It is also called. Okay. And you have learnt in previous lecture that this Ni is given at like this: 2 times of 2 pi kT over h square whole to the power 3 by 2 times Me star times Mh star whole to the power 3 by 4 times exponential raised to the power minus Eg over 2 kT. And what the different symbols represent in this expression, you know everything because you have studied this relation previously. You know here this K is a universal constant which is called Boltzmann constant. T is the absolute temperature. H is Planck's constant, which is also a universal constant. And Me star, you know, this is effective mass of electron, and Mh star is the effective mass of holes inside this crystal. Okay. Eg is band gap. Okay. So this is the expression for Ni. So if you know about the temperature dependence of the electrical conductivity of intrinsic semiconductor, then you must replace this intrinsic carrier concentration Ni by this expression. Okay. So let us put this value of Ni in equation A1, and you can see then sigma is given as E times mu n plus mu p times 2 into 2 pi kT over h square whole to the power 3 by 2 times Me star times Mh star whole to the power 3 by 4 times e to the power minus Eg over 2 kT. Okay. This is the expression for the electrical conductivity of a pure semiconductor at temperature T. And you can see from this formula that with increase in temperature T, this thermal conductivity will increase almost exponentially. Although here T to the power 3 by 2 factor is also present, but this exponential variation will dominate over this, and so we can say that when temperature of an intrinsic semiconductor is increased, its electrical conductivity increases almost exponentially. Okay. Actually, to get a concrete idea of temperature dependence of this electrical conductivity sigma of a pure semiconductor, we should take the natural log of this equation A2. So let us take the natural logarithm of equation A2, and you can see this will be ln sigma equal to natural log of E times mu n plus mu p plus log 2, you can see, plus 3 by 2 log 2 pi k over h square. Okay. And plus 3 by 4 log Me star times Mh star plus 3 by 2 log T. Here there is T to the power 3 by 2, and that will be, after taking logarithm, that will be 3 by 2 log T. And last factor is e to the power minus Eg divided by 2 kT, and when you will take log, this will be minus Eg over 2 kT. Okay. Now you can see, except the last these two terms, the remaining terms is a constant. So for the sum of the first 1, 2, 3 and 4, first 4 terms, we have written here constant. This has been written for the first 4 terms, which is actually a constant. Okay. And this last term has been written here, you can see, and the second last has been written here. Okay. Now actually this second term in the RHS is very small in comparison to the first term. In other words, you can say that the first term in this in the RHS of this equation A3 is a dominating term. It dominates over this second term. And so for an approximation, you can neglect this second term in comparison to the first term. Okay? So under this assumption, you can write that ln sigma is almost equal to minus Eg over 2k times 1 over t plus constant. And you can see this relation is just equivalent to y equal to mx plus c. So this is just equation of a straight line. If you will plot a graph of log sigma in against of 1 by t, at the place of y there is a log sigma, and at the place of x there is 1 over t. So when log sigma is plotted in against of 1 over t, then the straight line, a straight line will be obtained as you can see in this figure. Actually, I have projected this, and after projection it meets the 1 over t axis at this point, and this psi is the inclination of this straight line, and so its slope will be tan psi. You can see this tan psi will be negative because it is an obtuse angle. Okay. Now actually this minus Eg over 2k, this is at the place of m, which is called slope of the straight line. So actually measuring the slope of this straight line, you can estimate the value of band gap of this semiconductor, because you can see slope of this straight line tan sigma is equal to what? This is minus Eg over 2k. So Eg is equal to minus 2k times tan sigma. So if experimentally you obtain this graph and measure the value of psi, you can easily find the value of Eg. Okay? And so at a given temperature, by the help of this graphical plot, we will be able to estimate the value of band gap of the semiconductor. So logarithmic value of this semiconductor decreases with increase in 1 by t, mark it, 1 by, not reciprocal of temperature. So in reverse manner you can say when t will be increased, conductivity will increase. So the electrical conductivity of a pure semiconductor increases almost exponentially with rise in temperature. Okay. So this was a very simple discussion, and I hope you have definitely understand each and every aspect which I have discussed. But this is a very important fact, and your need for examination will be fulfilled after this lecture. It's my keen faith. Okay. Thank you very much.